Okay, I hope the audio is clear and the screen is shared. Let's start with. So today we will be doing with chi-square distribution. Last year you have done with the strong and low inequality, Chebyshev's inequality and central limit theorem. Now today we are going to do with the chi-square. So what is a chi-square distribution? The PDF of a chi-square distribution with n degrees of freedom is being given by 1 by 2, n by 2, n by 2, e to the power minus x by 2, x to the power n by 2 minus 1. Okay. So here it represents what? X greater than equals to 0 and n is equals to 1, 2. So here, to join, let's do join. So here, if chi-square, if a random variable, this is a formula, if a random variable x follows chi's distribution with this degrees of freedom, so then the chi-square with n degrees of freedom, what we write? We write x follows n square, or we say it n to the power 2. So there are certain important properties. First, I'm going to do them today. Who is joining? I guess all have joined. So here, I will, as I was explaining, that chi-square, still now people are joining. Okay, so what I was telling, I was discussing with the chi-square distribution. You have done with all the weak and law of large numbers. That one you have done. And what you have done, the central limit theorem you have already done. So now today I have planned to do with you the chi-square, all the distributions, starting with the chi-square first. Let's do. So I have started with the formula. Here you are having the chi-square with n degrees of freedom, which is being given by this formula, which you can see. Okay. So now this is a formula. Now there are certain properties of the chi-square distribution. Just let them do. So let us write it down. First, mean. Mean is n, variance 2n. So mean variance is 1:2. Okay. What is mode? Mode is so this one, what is mode? Mode is n-2. So here n is greater than 2. Now we have coefficient of skewness, that is beta 1 that is beta 1 is equals to 8 by n. Okay, so that comes to root over beta 1. Okay, so that is root over 8 by n. Now next come coefficient of kurtosis. So that is beta 2 is equals to 3 plus 12 by n, or we can say that is beta 2 minus 3. So that is 12 by n. Okay. Similarly, we have coefficient of variation. What is coefficient of variation? So CV is equal to by x bar. So root over 2 by n. Curl Pearson coefficient of skewness. Curl Pearson's coefficient of skewness. So that is m minus m naught by sigma. Okay. So that is root over 2 by n, that is greater than 0. So n is equals to 1 to this. So here chi-square distribution is positively skewed. Okay. And as sk tends to 0, so as n tends to infinity, that is for large degrees of freedom. So chi-square tends to be symmetrical. So here 8th one will be mu r. These are the properties which we are doing. X to the power r. So that is 2 to the power r n by 2 plus r by n by 2. Okay. So given r is 0, 1, 2. Okay. Now mean deviation about mean. Mean deviation about mean. That will be e to the power minus n by 2, n to the power n by 2 by 2 to the power n minus 4 by 2. 10 given. So here x tends to, so then m x, that is 1 minus 2t n by 2, given t less than 1 by 2. Okay. So here that is t. So 1 minus to the power minus n by 2. And there is a additive property of chi-square distribution. Okay. So the sum of independent chi-square variates is also a chi-square variate. Okay. So if I is equals to 1, 2, k are independent chi-square variates with degrees of freedom respectively, then summation I 1 to k, that is a chi-square variate, and that will be with summation of I 1 to k in I degrees of freedom. Okay. So that is xi will be chi-square, that is summation of I 1 to k xi, that is summation I1 to k ni if xi's are independent. Okay. And asymptotic normally. Asymptotic normality. So if x tends to, then z is equal to x minus expectation of x by sigma x. So that is x minus n by root 2n. So that will be n 0, 1 as n tends to infinity. So for practical purpose, like sigma square, that is n to n for large values of n. Okay. So for practical purpose, the approximation is fairly good for n greater than 30. But Professor Fisher proved the normal approximation of chi-square, where chi-square distribution is more pronounced if the instead of x, we consider the variable 2x, which is proved for n greater than 30. Let me show you here. That one is root 2x n root 2n minus 1, comma 1. So that tends to root 2x minus root 2n minus 1. That tends to n 0, comma 1. Okay. So n greater than 30. This is the important properties for chi-square distribution. Okay. Now, what are the critical values of chi-square distribution? Critical values of chi-square distribution. So there, let chi-square be the value for n degrees of freedom such that the area to the right of this point. So first, if we draw the diagram for this, here, square. So here, this is your acceptance region. Okay. And this is 1 minus, this is the critical value, this part. This is the critical value. And the chi-square, so this is the rejection region. This is 0. So the value which is known, just write it down. So here the value this is known as the If you see the graph, the upper right tail, okay, alpha point, critical value of chi-square for n degrees of freedom and has been tabulated for different values of n. Okay, and the equation was like this be the value of chi-square for n degrees of freedom, then the area to the right of this point alpha, that is here, this point. This is the acceptance region. Here you see the point. So this one. So that is P of alpha. Okay, which is shown. Now, some of the applications, if we talk about of chi-square, applications of chi-square distribution. So here, who developed this? So first, chi-square goodness of fit. Who developed it? Professor Carl Pearson in 1900 to test the significance of the difference between the experimental values and the corresponding theoretical values under same theory of hypothesis. Okay. So here, if suppose OI, okay, or I tends to 1, 2, suppose till n, these are the observed values, and similarly, the corresponding hypothetical values, say we take I equal to for 1, 2 till n, okay. So these are the corresponding hypothetical values. Now, obtained at the same theory or hypothesis, then under the null hypothesis, that there is a significant difference between what? Between the theory and the experiment. Okay. So there, Carl Pearson proved the statistic. Summation I1 given OI minus EI squared by EI. Okay. That is n minus 1. So 1 degrees of freedom is lost. Why? Because of linear constraint. So summation of I1, that is summation I1 to n, and expectation of I is n. Okay. That is your total frequency. Right? Now, if calculated value, if the calculated value of is greater than the supposed tabulated value, n minus 1, then we reject the null hypothesis. And at alpha level of significance. Okay. Otherwise, we will accept. Otherwise, it may be accepted if we cannot reject. So for practical, formula which is convenient, that is, write it down, summation of I1 to n by expectation minus. So that is summation of I1 to n, and here we have OI minus EI squared by expectation of I. So that is summation of I1 to n OI squared by expectation of I plus expectation minus 2O. So that is equals to summation of I1 to n I squared by expectation of plus summation of I minus 2 summation I O. Okay. So that is summation of I 1 to n by expectation of I minus n. So here, why? Because summation of I 1 to n, that is summation of I, that is equals to n. Okay. So what are the conditions for the validity of the goodness of it? So the conditions for validity of goodness of fit. First, n, the total frequency should be large, say greater than 50. Okay. Next, sample observations should be independent. Okay. Next, constraints on the cell frequencies are linear. Okay. Like summation of I 1 to n, that is summation of I 1 to n, that is equals to L. And no theoretical cell frequency should be small. So what I mean, if any theoretical frequency is less than 5, we add it to the proceeding or succeeding frequency so that the resulting frequency is greater than 5 and adjust for the degrees of freedom. This is one, this I told you about the goodness of fit, the chi-square test. But if it is for independence of attribute, then so chi-square test for independence of attributes. Okay. So here consider two attributes. What are the attributes? A and B. Okay. A classified into R classes and E classified into S classes. I'll make a big chunk. So here, let AI be the number of persons possessing the attribute, say AI. So I is equals to 1 to till R. Okay. And BI means the number of persons possessing the attribute BJ. So that is J is equal to 1 to till S. Okay. And AI BJ will be number of persons who are possessing both the attributes together. And the attributes I mentioned, AI and BJ, and that is also together. Okay. So these frequencies are arranged in a following R into S contingency table. How the table looks like? Let's draw it. In a big table, A will be horizontal and B will be the rows. Okay. And it like this A1, A2, dot, 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 AI. And here it will be P1, P2, again Pj, Ps, and finally you have the total. So if we draw it, so here, let's use another pen. Okay. So here for A1, B1, obviously we put it A1, B1, A1, B2, dot, dot, dot. This is A1, Bj. Okay, again A1, Bs. So total is what? A1. Similarly, for this one, A2, just you are putting down, like the matrix we do, correct? A2, B2, A2, Bj, dot, 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 A2, Bs. So that is A2. Okay. Here we get. Next, we are again having AI. So it is AI and B1. So AI, B1, AI B2, similarly AI BJ, AI BS, and total is AI. Okay. I hope you understand that part. Next, after AI, NET like term. So here also we end it. So here we have AR B1, AR B2, dot, dot, dot. This one I haven't given. Here also. Okay, these all are going because these are in series. So here it is A, R, B, J. And here also it is dot. And finally we have ARBS. And that is AR. That is the total. Okay. So now this is a table. Under the null hypothesis, H0 attributes A and B are independent. Okay. So expectation of AI BJ is equals to AI BJ by N. So that is AI BJ. Okay. So here, where summation of J is 1 to S, so that is AI BJ is equals to AI, or summation of I 1 to R, AI BJ is what? That is BJ. And AI is there. Initially, I told you that this both the attributes are together, number of person position. So we are taking this. Summation I1 to R, AI is equals to summation J1 to S, BJ, that is equals to R and S we combine. So we write it summation of I1 to R, summation of I1 to S, AI, BJ, that is equals to N. So using goodness of fit test, which we did, this is for the independence of attribute, the test statistic, the test statistics to test H0 in, for the equation, for the first one which I did, I give a star here, that is expectation of AI BJ, this one. So here we write it as in will be summation of I 1 to R, summation of J 1 to S, and that is equivalent to AI BJ minus AI BJ 0 by AI BJ 0 square. Okay, that tends to R minus 1 and S minus 1. That is equals to summation I1 to R. Obviously, again, J will be 1 to S. So AI BJ squared by AI BJ minus what we, so finally, which I told, if calculated is greater than the tabulated for R minus 1 and S minus 1 at significance level. So what we do, we reject H0 at 5% level of significance. Otherwise, what it will be? Obviously, it will be accepted. Otherwise, it may be accepted. Okay. So now, degrees of freedom. Degrees of freedom I am telling. So it is DF, we can write, correct. So it is abbreviated. And it is the what? It is the extent of independence enjoyed by a given set of observed frequencies. Okay. So here if I write the formula, so then DF is equal to number of observation minus number of independent constraints on them. Constraints on them. Okay. So this is for the table which I did for you, contingency table. Okay. So the total number of observations will be R multiplied by S. Okay. Now, what are the constraints? I'm talking about constraints. Let's define them. So the constraints are 1 R. R is what? The R row totals fixed. Okay. R constraints. And second is S. So that is columns totals fixed, S constraints. Okay. But this R plus S constraints are not independent but subjected to the constraint. So that is summation of Ri, Ai is equals to summation of J1 to S, Bjn. So that is one constraint. Okay. Then what are the number of independent constraints? So number of independent constraints will be R plus S minus 1. And the degrees of freedom for RS table, that is RS minus R plus S minus 1. So that is RS minus R minus S plus 1. So that is R minus 1 multiplied by S minus 1. Right, by S minus 1. This is one. Next, the coefficient of mean square contingency. Mean square contingency. So that's how we calculate for the same. This is mean square contingency. Okay. So that is being calculated as C is equals to square plus N. So that is root over by 1 plus, so given that is by N. Okay. And for a 2 cross 2 contingency table, because just now I have shown you the table. So for a 2 cross 2 contingency table, like this, we have A, B, C, D. The value will be given by N AD minus AB square by A plus B, C plus D, A plus C, B plus D. And here, what is the N? N is A plus B plus C plus D. Okay. Now, Yates correction for continuity. That is there for this. So, what is that? Note it down. Yates correction for continuity. Okay. So for a 2 cross 2 contingency table, so here degrees of freedom is 2 minus 1 minus 1. So that is 1 cross 1, that is 1. Okay. So if any one of the expected frequency, which I was telling you, is less than 5, then it is to be pooled with what? With the succeeding or the preceding one. so that the resulting frequency is what? The resulting frequency is greater than equals to 5. So this pooling technique results in a loss of 1 degrees of freedom. So then the effective degrees of freedom goes 1 minus 1, that is, which is meaningless. Why? Because in this case we compute, if you see, after applying F Yates correction for continuity, which I am explaining. So in this case, which consists in adding, it is 1934, okay. So here, which consists in adding 0.5 to the cell frequency, which is less than 5, and adjusting the other frequency in the 2 cross 2 table. So 2 cross 2 table, so that goes A, B, C, D after applying Yates correction. Got it? So that is, it looks like the formula AB minus AB minus this one, not n by 2 square by A plus B, C plus D, A plus C, B plus D. Okay. Next, chi-square test for population variance. Very, important topic. We know sample statistics, we all do. So population variance, we have to. Suppose we want to test if the given normal population has a specified variance. So how we do that? See? Okay. So then let x1, x2 till xn be a random sample. P. Okay. So now from a given normal population, that is n, this. So to test, again we get null hypothesis and alternative hypothesis. So there it is, sigma square. So the test statistics will look, the test statistics will be sigma. So that is summation I 1 to n xi minus x bar square by, okay, so that is ns square by this. It follows a chi-square distribution. Follows chi-square distribution with n minus 1 degrees of freedom. And by comparing this value with the tabulated value for, n minus 1 degrees of freedom, what we get? At a certain level of significance, we may accept or reject. Okay. For chi-square, today I will give you another more theory, that is Bartlett's test for testing the homogeneity. Bartlett's test for testing the homogeneity of independent estimates. Testing the homogeneity of independent estimates. Okay, of the same population variance, or you can write to test sigma 2 till k. Okay, that is, so suppose let xij be j say 1 2 till n, okay, and I say 1 2 till k. This be k independent samples from a population, say population. So here under, again we go to testing. So we state it as Sigma, which I already told you, it will be till how much? K equals to, and that will be equals to this. So the test statistic is, we write it as summation of I 1 to k ni minus 1. So that is log of s square by si square. Okay. By 1 plus 3 by k minus 1. So summation of I, that is 1 to k here. Okay. 1 to k, 1 by ni minus 1 minus, I am writing it down, it will be together here, minus 1 by summation of I ni minus 1. This together. Okay, till this much. So where this is a formula, here SI square is what? SI square is 1 by ni minus 1 summation of j 1 to ni. So here xij minus xi bar. So that is I is 1, 2 till I have taken here k. So, and s square is summation of I 1 to k. So ni minus 1 is I square by summation of I 1 to k. So ni minus 1. So here, and it follows chi-square distribution with k minus 1 degrees of freedom. And follows chi-square distribution with k minus 1 degrees of freedom. So by comparing this calculated value of sigma square with tabulated value of this for k minus 1 degrees of freedom, at certain level of significance, say alpha, we may reject or accept H naught at that level of significance. Okay. So these are the 4 types of chi-square types which are there, which we get. There are certain important theorems for the same. We will do them. First, let's do some questions. Okay. So for the question, let me write one question here. So here, first, which one of the following is not correct? If I ask you, first, the mean, let's do MCQ. The mean of chi-square distribution with degrees of freedom is n. Next, the variance of chi-square distribution is minus infinity to infinity, or the range of chi-square distribution is 2n with n degrees freedom, or D, the MGF of chi-square distribution with the degrees of freedom is, I hope the options are visible to everyone, 1 minus 2t minus. So which one will be the answer for this? Anyone?
MGF, ma'am.
MGF. So the correct option is option D, you are telling me. Okay. So here, if you see all the statements, I'm telling you which one of the is not correct, I told you. Correct. Which of the is not correct. So I have given you the definitions. So here, all the statements except C are correct. It's MGF. I mentioned in today's class. Okay. Just revise that. We will show you the notes of chi-square with the degrees of freedom. It's 1 minus 2t to the power. So C is your correct option. Okay. Let's try the second one. I will give you more questions. So here, question, say, will give you, okay. If this is a question, say if x1, x2 are identically and independently distributed. So random variables, then p of x1 squared plus x2 squared is less than 2 equal.
Hello, ma'am.
Yes, tell me.
Ma'am, in the previous question, the option was given that variance would be from minus infinity to infinity. Will that be a correct option, ma'am?
Which one?
B option. I guess option B would be the, because variance is always positive, no, ma'am?
Yeah, variance is 2n.
Yes. So which
So
one is the
option
correct
B.
answer?
Option B.
B.
Option B. Option B is the
Yeah.
correct answer. Yeah. Option B is the correct answer. The range of chi-square distribution is minus infinity to plus infinity. That is the correct option. All options except option B are not correct. Anyone? Any more questions? Okay, next one. If x1, x2 are identically and independently distributed, so here, then p x1 plus x2 less than 2 equals to what? A e to the power minus 1, b 1 minus e to the power minus 1, c e to the power minus 2, and d 1 minus e to the power minus 2. Then, which one will be the answer?
Ma'am, in the first question, I think even range is from 0 to infinity, I guess. So it will also be wrong, right? Then we'll have
Which
two
one?
options. Range of chi-square distribution is...
No, no, no. The range of chi-square distribution is 2n, I told. 2n. See, 2n with. So this is not a correct answer. This one, except this, all are. I have told which, first understand which one of the following is not correct. Okay. So here the first option I have told, the mean of a chi-square distribution is n. Okay. This one is correct. The variance of chi-square distribution is minus infinity to infinity. Yes. This is not correct because we have done today the graph, correct? This one, the range of chi-square, no, it is not. This one also only is the correct answer. And the question, which one of the following is not correct? And the MGF we told, that is also not.
Okay.
Okay, yeah. Only that one is. Okay. Next, for question 2, okay. This one, I hope everyone have noted the question. If x1, x2 are identically and independently distributed, then P will be equals to what?
Answer B.
B. Option B. That is 1 minus e to the power minus n. Okay. Rest all what are telling. This one. Okay. Let's do. So xi identically and independently distributed. So n will be 0, 1. Given I is 1, 2, and that is xi square given sigma, which we did. Okay. So here x is equal to x1 square plus x2 square given sigma. So 1 plus 1, so that is 2. Degrees of freedom by the additive property. Okay. So here PDF of x, we will find it out. So PDF of x, so here fx is equal to e to the power minus x by 2, n by 2 minus 1. So here by 2 to the power n by 2, n by 2, so n is equals to 2. That comes to half e to the power minus x by 2. So x greater than 0. Then probability of x1 square plus x2 square less than 2. That is coming to half is equals to p of x less than 2. So that is half of integration 0 to 2 e to the power minus x by 2 dx. So that is equals to half of e to the power minus x by 2 by minus half 0 to 2. So that's the correct answer. Very good. 1 minus e to the power minus 1. Okay. Next to another question. So this correct option is option B. Next question will be, if a question comes like, let x1, x2 till x10 be identically and independently distributed. So n is 0, 1 random variables. Okay. So if t is x1 square plus x2 square plus dot 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 plus x10 square, then expectation of 1 by t will be equals to, I hope you have seen the question. So it will be 1 by 5, 1 by 6, 1 by 8, 1 by 12. What it will be? Who will tell me this? So here xi's are identically and independently distributed. So n is 0, 1. So t is summation. Yes, anybody is telling anything?
Ma'am, I got 1 by 8.
Which one?
Answer.
Yeah, answer which one? You are telling me.
I forgot the option. I got the answer as 1 by 8.
1 by 8. Okay, let's see together. 1 by 8. I took it. Okay, I have written it. Okay, let's see. So here, I 1 to 10. So it's summation. Okay. So here it will be given 10. Okay. So here ft will be, you have to find it out. So that is 1 by 2 to the power 10 by 2, 10 by 2, e to the power minus t by 2. I'm writing it here. For space, you have to write it. So it's 10 by 2 minus 1. So that is 1 by 2 to the power 5, 5 e to the power minus t by 2, e to the power 4. Okay. So here t is greater than 0. So expectation of 1 by t is 1 by 2 to the power 5 given 5 0 1 by t e to the power minus t by 2 t to the power 4 dt. So that is equals to 1 by 2 to the power 5 0 to infinity e to the power minus t by 2 e cube dt. Okay, so that is 1 by 2 to the power 5 of 5 or 4 half of 4. So that is equivalent to half of 4 by 4, that is equals to 1 by 8 gamma infinity. Good. So the correct option is 1 by 8. Who told me that is the correct option? Okay, that is the answer. Now, the last question for today we do. So here, let x1, x2 till xn be a random sample. Okay, from n mu this. So we have to define x is equal to 1 by n summation of I1 to n xi, and a is equals to summation of I1 to n xi square. Question C. So then which one of the following pair will be independently distributed? So here a x bar, b will be a minus n x bar squared, c will be a minus n x bar and d will be a x bar square. Seen the question? Who will tell me the answer now? Please be louder, whoever is saying the answer.
Maybe A.
A. Okay, let's see. All A. All are telling me, whoever are telling me answer A. Seen the question? Just see the question once more. In a random sample, x bar is 1 by xi and s square is this. Then what will be the answer? And these are the answer. So which one it will be? Okay, let's do A. Okay, so I've written it. A. Let's see. So in a random sample of size n from n mu sigma square population. So here x bar is 1 by n summation I 1 to n xi. Okay, and what is the s? S square is 1 by n summation of I 1 to n. So xi minus x bar square. Okay, they are independently distributed. Okay, so s square will be 1 by n summation I 1 to n xi square minus x bar square. That is equals to a by n minus x bar square. So that is 1 by n a minus n x bar square. It's inside. It means different. So it's inside, okay? Square. So A is what? A is summation of I1 to n xi square. Okay. So x bar is square independent. So that means x bar and a minus n x square are independent. So which one will be the options? The correct option?
C.
C is the correct option. Got it? Who told me that the option A? Why it is C? Clear? So any question anyone having from today's class? No? Okay. Thank you then.